We're going to look at pressure vessels here, and basically when a vessel of some sort is under pressure, it's got some sort of pressurized fluid in it. What it does is it creates stresses and makes the material loaded in all directions as it pushes out. Okay, and what we use in pressure vessels is we actually use a gauge pressure. And this is the pressure above the atmospheric pressure. And that's because, well, the atmosphere is pushing in the same amount as it's pushing out. So that it basically cancels itself out. So all we're really cared about is what the pressure is above that atmospheric. Because, again, on the outside, there's that atmospheric pressure pushing in on it. So what we look at here are thin-walled, and what we basically define thin wall as is the radius over the thickness. That ratio of the radius to thickness is greater than 10. Okay, so if the thickness is less than 1/10 of the radius, that's what we're talking about when we talk about a thin-walled pressure vessel. So let's first look at a cylinder. We're also going to look at a sphere. But if I look at a cylinder, there's basically two directions I can have stress occurring. One is a longitudinal stress, and that would be the stress directed along the length of the cylinder. Okay, so basically if I cut it and think about a force balance, okay, I have this ring, the circumference times the thickness of the vessel. Okay, that is the area. If I take that times the stress, that creates the force in that ring that I have there. Okay, and that has to balance with the pressure that's on the inside times the area of this circle, which is going to be pi r squared. So again, I've got that pressure in here. That balances with the stress in the ring, and I get that. Solving for that stress, we call this the longitudinal stress, is the internal gauge pressure times the radius over 2 times the thickness of the wall. Okay. Now, in the other direction, I have what we call hoop stress. Okay, so if I cut it this way, okay, my stress occurs in these two small little areas right here, which is basically defined as, the wall thickness times some arbitrary dy that I cut out of this thing. Okay, so that's the area. I take that times its stress, which again we're calling the hoop stress, and take that times 2 because I have one up here and I also have one down here. That balances with the pressure of this area right here, which is essentially the diameter 2r times, again, that arbitrary thickness dy, the pressure pushing out that way. Solving that for the stress, I get PR over T. Okay. Now notice that the hoop stress is actually twice as big as the longitudinal stress. So generally that's the stress we're more concerned with in a cylindrical pressure vessel. Now in a sphere, it's all symmetrical, so it basically asks very similarly to the longitudinal stress that I did previously. Okay, so again, that area inside times the pressure has to equal the stress times the area, which is basically the circumference times the thickness of the wall. And again, that's going to work out to PR over 2T. And again, that is in all directions because a sphere is symmetrical, so no matter which way I cut it, I'm going to get the same stress going in all directions, as opposed to a cylinder where the hoop stress is twice as big as the longitudinal stress.